this lecture we will discuss on second isomorphism theorem. So let's first discuss the statement of this theorem. The second isomorphism theorem states that let G be a group and H be is a subgroup and K is a normal subgroup. Here there are 3 points. G is a group, H is a subgroup and K is a normal subgroup of G. These are two subgroups of G. This is a normal subgroup, simple subgroup, and K is normal subgroup. The first point is we will show that H intersection K is a normal subgroup of H. Second, the HK is a subgroup of G, and the second is quiescent group obtained by H upon H intersection K, which is equivalent to HK upon K. This will be equivalent to HK upon K. We will show these 3 points. So first to discuss the first point. So in the first point we will see H intersection K is a normal subgroup. So we will check this point. So to prove this point, first we suppose that H upon K, H intersection K is possible and there is an element which is X and this element is available in the intersection of H upon H intersection K. If it is available in H intersection K, then it will be available in H as well as it will be available in K. As we know that K is a normal subgroup. We know that the K is normal subgroup and we also know that the property of normal subgroup that for any element X, the X A inverse, this will belongs to N. This is the property of normal subgroup. So here the H inverse will belongs to K because K is normal subgroup. Here we are taking any element from H because every element of H is belonging to G. So this property will be satisfied for every element of G if the K is normal subgroup. Again, because this is belongs to K and K is a normal subgroup of G, and K, every element of K will belongs to in H because the K is a kernel which is generally containing the elements which are mapped on identity. Now we wish to prove the second property. The second property is HK is a subgroup. So let us see on this property. Let us suppose there are 2 elements which are belonging to HK. These are 2 elements because H and K, these are 2 subgroups and this is the product of 2 subgroups. So what will be the nature of the element of because it is product, so the first this will be the element of this HK will be the composition of the element of H as well as the element of K. So let us suppose H1 is the element of H and K1 is the element of K. So HK1, this will be a closure composition and that will be available in HK because HK is the product. So here we will take the product of their elements individually. Similarly, the HK can be defined, X2 can be defined in terms of H2 and K2 where H1 and H2 are belonging to H and K1 and K2 are belonging to K. And now we want to prove that this is a subgroup and the property to prove a set as a subgroup is sufficient. The sufficient property is AB inverse is belonging to H. If you could see the AB inverse is belonging to H, then this H will be a subgroup. This is the sufficient property and this theorem we have studied in our topic subgroup. So here we are taking what will be the result if you could calculate x1 x2 inverse. We are substituting the value of x1 and x2. After that here we are using the reversal law. After applying the reversal law we are applying here the associative property, and in associative property the composition of every 2 elements will be satisfied by closure because K1 is the element of K and K2 inverse is the element of K. These are 2 individual element of K and K is a subgroup, so their composition will be possible and this will give a new element. So this is new element is here noting by K3. So again I am writing it as H2 inverse and H2. We are multiplying this term here because H2 inverse and H2 this is equivalent to identity, so no effect will be obtained here. I am again applying here the associative property, and after applying this associative property we are seeing that this is the element of H while this is the element of K. So on multiplying the element of H with the element of K, the resultant will be available in HK. So here the AB inverse, the type of this composition, which is the type of this AB inverse is available in HK. So this HK will be also a subgroup. Now the next property is to prove that this quiescent group is equivalent to this. Now we will prove this property. So first we will define a mapping for this, and here in this mapping we are assuming that the mapping of the element H is available in Hk upon K, because here we are multiplying and divide both side by K. So this is nothing new, this is equivalent to H, and here we are taking this mapping as phi. So what will be the nature of the set H? We will take the small H1, H2 and so on. So here we are taking the element H and we are applying the mapping phi on that element, and the resultant will be of the type HK by using this property. So this is our first property. So here we can say that the mapping phi is well defined, and this is onto also. Again I am applying the this mapping on the composition of two element H1 and H2. This is phi, and as per the definition which is mentioned in equation first, the phi of H, the mapping of any element will be available, will be equivalent to HK. This is small h and this is K. This is the HK. So here this H1 H2 will be multiplied by K as per the equation first. Now we are applying the associative property, or you can write this K as KK and you can apply the associative property, or this is the definition of normal subgroup here. So it is individually can be written as phi of H1 and phi of H2. This is again by equation first. We are again applying the equation first here in 2 points. So here we are seeing that the mapping of the product of two elements is equivalent to the product of their mappings. So here we can say that this phi is a homomorphism. After proving this phi is homomorphism, we can say that this phi is epimorphism because it is a homomorphism and also it is one on two. So it is a epimorphism. And here we can apply the first isomorphism theorem if the map phi is homomorphism and it is onto also. So on applying this property, this is the statement which we have discussed in first isomorphism theorem. This part is equivalent to this. So here we can write the third property or third result directly. But in this case we have to show that this K is a kernel or not. So to prove this K is a kernel, we have to add this extra activity which we have discussed in our previous theorem, which is related to kernel of a subgroup. And in this part we are taking any element H on this mapping is K, and after here we are applying the property first, equation first, that will be equivalent to K, and here we are seeing that this H will belongs to K. By this property we can say that this H belongs to K, because this H is belonging to H as well as it is belonging to K, so it will be available in H intersection K. So here we can say that the kernel of phi will be available in the intersection of H and K. The kernel of phi is the set of element that will be the subset of H intersection K. Again we are taking any element in this intersection, and we are again showing that every element which is available in H intersection K, that will be available in kernel of phi. So here we are taking this property second and property third. By this property second and property third, we can say that the kernel of phi will be equivalent to H intersection K, and the kernel of phi can be again defined by H upon kernel of phi and Hk upon K. Here we are applying the property, second property, and by using this and on rearranging the terms from this equation, we can write this result. This is the third statement of this theorem. I hope you could understand the second isomorphism theorem, and in next lecture we will discuss the third isomorphism theorem, which will be the last topic of our syllabus. And if you are facing any difficulty to understand this theorem or first isomorphism theorem, you can contact me anytime. And we will take some doubt session also uh, with after uploading this video, and in that doubt session I will ask about your doubts. So study this theorem carefully, because these three theorems are very important, and at least one from these will be asked in your entered examination. Thank you so much.